starting now. So we have the recording for our last final review session for the semester. And just before this recording began, we talked a little bit more about the test overview. And I'll just want to summarize this one more time for anyone who might be watching the recording that wasn't in this discussion. We have 3 hours for technical, 3 hours for written, and the written will be based on the technical analysis. So I would expect you to have your technical notebook open, and then there will be 6 questions that are interpreting each of the case studies, and then 4 questions that are more theory-based and would be using one of the case study questions as supporting evidence. So if you're seeing this recording and you have more questions, feel free to reach out on Slack. Otherwise, this information should be pretty straightforward, and it's in this notebook that you all have access to. So tonight we will start our review session with some of these questions that were requested ahead of time. And with that, even this last 2 questions, I might get into some further concepts, really just to extrapolate some of the things we've done in this class and where you might be going next. So it might not be relevant to the final exactly, but I'd be happy to talk through it if students are interested. So this first question we'll be talking through is showing a box plot. So I'm just going to make sure I have all my packages run for this. And feel free while I'm walking through this, like, please interrupt me if you want to talk through something. For some of the students who've joined some one-on-one sessions for talking through the data wrangling, like if there's other Python related questions too, you know, this is our last class together, so take advantage of the opportunity to ask more questions. But specifically, we're going to show how we create a box plot. And I'm just using one of the homework examples where we had to do, I assume it was ANOVA, where we were looking at different brands of car and if it was in a garage or not, with the goal to see if garage type increased the longevity of the car. So maybe this was number of years in different brands. So I assume this was our two-way, like 2 interaction ANOVA test, but we're just going to use this to show the box plot and how to do it. And we wrangle this using MELT. I looked into this a little further because last review session, there was the question of what's the difference between MELT versus stack? And really the key lies in how many columns are we trying to pivot into this format that is conducive for the ANOVA test, where if we only have one column that we want to wrangle, so if this was a one-way ANOVA, we could actually use both stacked and MELT, they would be equivalent. But when it's 2 different variables, we need to use .MELT. Otherwise, the wrangling will look like this. So we'll talk through this a little bit more. So, because this is part of making a box plot, I assume you'll have data that looks very similar to this. And you would need to wrangle it in a way for an ANOVA test. And then part of that ANOVA test will be plotting the distribution using a box plot. And it'll be specified, make a box plot for that. So let me just show you what it looks like, because this is just, we're tying a couple of loose threads from the last review session as well. So this is how it would look like using MELT, where our goal is to have each combination between garage and the brand and the value. That's really the purpose of getting this ANOVA ready, is because we want to see for each pair that we are comparing, what is the value? And then we're just aggregating all of those things and taking the difference in the residuals for the mean squared error with the variance. And that's really what the ANOVA is doing. So it needs it in this format. And if we use stack, check out how this looks, where it got things confused with garage. Yes, there's multiple levels. So therefore, we can't use just stack when we have 2 different variables. But, if this was a data set you were facing in the world, I would assume you could just play around with it until you got it to what you needed it to look like. And you would see, hey, this wouldn't work. Any questions just on this? I know we haven't gotten to the box plot specifically, but this touches on some other concepts that folks were interested in last time.
So what exactly did you do to make it only to make it look different again? I'm sorry. I looked away for a quick second.
Yeah, no worries. This gets into comparing between melting a data frame versus stacking. So this is the question we are answering right now is what's the difference between melting versus stacking? Because in some of the demos, I've done both. Because we'll see the theme for tonight is there's lots of ways to peel a potato, and there's different ways to do it. There's no correct one. It's more so as long as what you did made sense. So I believe the question was, what are we doing to the data? It started off like this when we just read it directly from the link here on Excel. And we have these different categories for what the car would be. And we have if it was in a garage or not. So just imagine this was in the real world and you went as you manufacture cars and you want to know, your brand, or maybe you're, a car salesperson and you want to be able to tell your clients, hey, choose this brand over this one and get these tires and make sure, you keep it in a garage because it's proven that the longevity will be longer. So we're trying to test this theory. So we have different observations. And perhaps we have, when it was in a garage, brand A lasted 7 years, B 6, C 8. And our goal is to test if there is a significant difference in the variance of the longevity of the car, if it is brand A or B or C, and if it was in a garage. So that's the purpose of what we're doing with this data and why you might get the data in this format where you have each observation. And that's why we need to wrangle that data in a way that gives us the interaction between being in a garage and the brand with this number. So we're almost creating lots of little pivots for each combination. And that's why we need this melt function. Because if we look to see what this is actually doing, similar, if anyone enjoys Excel and is very comfortable making pivot tables, this is a similar function where we're creating a pivot, or you unpivot the data frame where we massage it into this format that's conducive for our ANOVA analysis. Did that answer your question, or maybe you were getting a different aspect?
I get it now.
Okay, perfect. And then just to conclude that answer, when we massage it in this way, it gives us the pairwise combination and the value. And that is what we're using in the ANOVA to compare if there is a significant difference between when there's brand A and it's in the garage, compared to brand A when it's not in the garage. Because we're essentially aggregating all of these values as a sample for this group, similar to when we were comparing wheelchairs. We're looking at these different groups within sample and then between samples, and we're seeing how much does the variance compare. That's why we need it in this format, because we're seeing between these groups and the interaction with this other group, what is the value. And the reason why when we stack it, this wouldn't give us the right format is because it does other stuff with it that we just can't work with because it has this column. It's just not clean for what we want to do. If you wanted to further wrangle this to get it in a format like this, it's not impossible. You could do it, but this is just the most straightforward way to do it.
And if you wanted to make it so the value is ascending, you would just do sort by.
Yeah, I like this question because it gets back into some other concepts we learned. So if you wanted to sort this in ascending, so let's say, your question was which combination gives us the longest longevity? What would you do here?
I would probably do value. That's the only one that makes sense to me.
Nice. Yeah. So when you have this by, because it wants to know, what are you doing it by? Okay, maybe it's not by. I think it's this one. Oh, my bad. It's sort values by. And this, by default, it sorts it in ascending order, so from smallest to largest. But if we wanted to get it from the largest to the smallest, we could just change that. And now this is at the top. So, you know, similar back to the midterm, you won't need to do this on the final at all, but I think it's just helpful for us to still review these things. You know, now we could say, okay, brand C, when it's in the garage, you know, this almost gets a little bit at what we would expect to see when we do the box plot. You know, this is in tabular format. So it is good to always, you know, have these tools in your belt so you could double check yourself and kind of like sanity check to see, you know, okay, if we get a result that says brand C and in a garage is something meaningful, like it makes sense. Okay, both of these have the highest value as a pair. So moving on to the question at hand, and this is a little bit more information that I just talked through regarding the difference between these two things. And again, if you access the link that is shared on Slack, you can have this content to refer back to. So what we have now, we're not going to use this. I didn't even save it as a variable because it was just to show you that it produces garbage that we can't work with. So we are going to use this melted version, which gets us exactly what we're looking for, all these different combinations. And so let me just bring this back here so we can see what it is that we're going to work with. Because now the question we were answering is, how do we plot this in a box plot? So right now, by default, when we melt it, it changes the columns names to these just like innocuous labels. So we have variable and value, but for interpretation's sake, and when we plot it, it might make our lives a little easier to change the names to be something a little bit more intuitive, especially getting back to real life. If you ever hand someone a data set and they have no idea what variable and value really mean, it's always better to be a little bit more specific so that that transfer of knowledge doesn't go haywire. You know, for example, even like units being different, if you're talking metric system and someone else is in another unit system, it's always good to be more specific about the data itself. But again, this isn't like a data governance class, but there's lots more to think about. So we changed the column name using this function of take my data frame, rename these columns. I have it in place, so it didn't return anything because it did this function on the data frame itself. And so now we see instead of variable, we have brand and value. You know, I could have changed this if we wanted to be even more specific. I could make this into like longevity. And now if I ran this again, I'll see I changed the name of the column to be longevity. Or maybe, you know, years. It's up to you as, you know, as the person doing the analysis. And now that we have the data in this format from melting it, we can use just this one line of code right here. And this is using seaborn.boxplot. So that's why you needed to import that up here. We could have also used the default matplotlib. This is again going to our theme of there's lots of ways to do something. No one is right, but this is one approach that makes it pretty easy and perhaps aesthetically more pleasant than just out of the box matplotlib. So that's why people use Seaborn. It comes with a lot of bells and whistles kind of by default, where it makes this formatting a little nicer because you get to choose these palettes. That's kind of why. So you would input which variable are you trying to compare between as the independent, and then what is the dependent on the y-axis. So we would say we're trying to look for, you know, now it was value because I changed, you know, if I did this, it would say, I don't know where value is. And that's because it's no longer the column name. Now it's longevity. So if I change this back here, and now I have it working to say between brand A, B, C, which one had the most, the longest longevity in years. And even back to that question about sorting, we saw brand C had some of the highest ones. So this makes sense. And if we wanted to look at the other variable of if it's in a garage or not, we would use that here. Any questions regarding how to make a box plot or how to interpret these things? Because even it'd be good to know, like, what does this middle line mean? If we saw diamonds here, there might be some, what would diamonds?
Outliers.
Yeah, nice. Yes, exactly. Outliers. So nice job. Yeah, so this shows us the distribution. So, a caption would be, I see brand C is higher. There's no outliers here. We see relatively like the median value is higher for brand C and much lower for brand B. And then here, there's no line. Can anyone guess why there's no horizontal line when we're comparing these different things?
Is it because there's no median or mean that's been observed?
You know what? Yeah, I'm trying to think also why there is none myself, because probably maybe it is just this constant value. Let's even just see, if we group by, I'll look into that one a little bit more, because why wouldn't there be? That's something you could put as a caption. I won't go into it too much more because I want us to have time for other stuff, and we are. So anyway, that was a bit of my own tangent. So yeah, for your own sake, I would look into this further. For my own sake, I'm curious. But just for the sake of time, we won't talk about it too much more because I want to get into this other question. But any other just technical questions regarding this, concerns with making a box plot that we'd want to discuss?
There was a question in the chat. I don't know if you saw it or not.
Yes, but these seem a little bit less related. So I want to get to everything. I just want to make sure that we covered our bases for this. But thank you for pointing that out. Yeah, we'll add that to the docket of questions to answer. Because some of these we'll touch to, like that first one of why do we set a seed when creating a random sample? That was exactly what I was going to get to next. So just any other questions regarding box plots? Alrighty. So next we will talk about this question that I also saw Mara posted. Why do we set a seed when creating a random sample? And this also relates to reproducible research. So let me just grab the specific question that was asked, just to make sure I have the wording exactly, because I think it was an excellently worded question as well. And the question was specific. Oh, okay. I think they actually just copy and pasted something that I had there. But anyway, it's kind of like what's the sample size and how does it relate to reducible research? Why do we set the seed when creating a random sample? So I think I just tooted my own horn because I like that someone, these concepts are related to setting the seed, taking a sample, as it relates to scientific research and making sure that our work is reproducible. So let me just take a step back and put this question here so we can talk through it a little bit more, because this would be an example of one of those theory related questions where it'd say, like talk about, representative sample as it relates to one of these questions in the case study. And these would be some items you'd want to talk about when it comes to reproducible research and sample size. So, and then setting the seed. So let's just talk through these three separate things of sample size, reproducible research, and setting the seed. So maybe first, can anyone tell me how this even relates to sample size and like why sample size matters. Like what is the purpose of taking a sample?
Because you can't test an entire population, so you take a sample to make an assumption on a representation of the population.
Yes, exactly. And I like some of the words you use too of like representation of the population, because it's not feasible to ask every single person or, you know, take that full population measurement. So that is why we take a sample, and you mentioned it needs to be representative of the population. And in order to make sure it's representative of the entire population, we need to make sure that our sample size isn't like a very biased selection where perhaps, you know, if we're looking to see like, would my new menu change the amount of food someone would order? But meanwhile, I only ask people who are in my restaurant, who, you know, come pretty often. That would be a pretty small sample size and not representative of the population of all, you know, potential customers. And having a sample size large enough that it represents the real population that you're going after is part of our analysis. And a lot of the different hypothesis tests take into account what is the sample size for calculating that test statistic. So you'll see anytime we divide by n, we're taking the number of observations into account because we're less certain of our reliability the smaller the sample size is. And we have more certainty when there's more sample size. So that's why we divide. It almost like penalizes us more when the sample size is small and penalizes you less when the sample size is really big. And getting back to what Joshua was talking about, for making sure our sample is representative, we're more likely to misrepresent our population the smaller the sample size is, and less likely when it's larger. And this relates to the central limit theorem of the more observations we have, we now can use probability to say the likelihood of seeing this value given the frequency of seeing it. So that is part of why we take a sample and make sure it's large enough, because a lot of the statistics we're doing hinges on the reliability of that probability distribution. And so similar to that Plinko example, when we only ran 10 observations, we might see lots of outliers and there's no real pattern for us to form a basis on. But when we ran that simulation for hundreds of thousands of observations, we started to see this normal distribution that therefore can be used to test a different hypothesis, because we now have a large enough sample size to use our statistics with. So that even relates to when we were getting into some t-tests, when you had student start making smaller sample sizes, and that's why we use the t-distribution instead of the normal distribution, because this was a way to overcome that limitation of having the data be normally distributed for us to use our assumptions of symmetric distribution of area in the tails. And so that's why the whole novelty of what William Gossett did of making this applicable to smaller samples is because of the t-distribution that he calculated. So that was very long-winded, but kind of touches upon a lot of different concepts of why sample size is important and how it represents the population, and some of the considerations as it relates to researching things and framing an experiment. Any questions about sample size before we talk about these two other concepts? Okay.
No.
Thank you for the feedback. I appreciate the two-way, because this is only as good as what you guys want to see. And if I'm just rambling on things that also don't seem important to you, also feel free to, ask more pointed questions.
Yeah, you did a great job. You explained like everything to like the smallest detail.
Okay, I appreciate that. Thank you. Thank you. Okay, so sample size now, talking as it relates to reproducible research and setting the seed, which this is one of the first principles we taught in the first lecture of our class, was talking about how do we even know anything about the world? We create models to represent how things work. And we introduced this concept of, Occam's razor too, of when we were trying to model how the planets spin around the sun and such. So like kind of the most simple model that stands the test of time is usually the best solution. So I bring up this concept just to tie it back to our whole class of reproducible research and why it's important to make sure that anyone else can take your experiment, see the steps that you took, and recreate that experiment again in order to progress scientific knowledge. So even if you created an experiment, like in one of your bonus point, case study analysis, and the results of your hypothesis was to, fail to reject the null hypothesis, like you didn't, find evidence to support the alternative, that's still a discovery, that's still pushing new knowledge forward. And it's important that someone could take that research and grow from it. They said, okay, maybe this didn't result in something interesting, but what if I now look at this thing? I want to augment the data analysis you did and do something more with it. So therefore, it's really important that you acknowledge the bias of what went into the data, any decisions you made, assumptions. But when I talk about reproducible research, it's very important to be transparent with what you did and not necessarily like skew anything in order to just make a conclusion that's, publishable by, a research, for funding, kind of getting more into like academia and how sometimes there's a concept of p-hacking where you might just change minor aspects of your analysis in order to find a significant value in your hypothesis test so that, you can publish it and lots of people read your publication. But that's not scientific. That's really driven by something else. So that gets into reproducible research, which hinges on this concept of setting the seed whenever we take a random sample. And I'll just walk through what that looks like. But the reason we set a seed is so that if someone were to emulate our research, and, let's say I found a p-value that was super significant in my little case study, and someone says, no way you found that, like that doesn't make sense to me. They could go through what I did and recreate those results and validate it essentially. So this really just gets into taking what we're doing in an experiment, in a statistics class, and bringing it into research to progress society in a way that is measurable and reproducible so that someone else can validate whatever discovery you made. So I'll just show you what this looks like in the final. You won't have to do this either because I will have done it for you of like taking a sample. So this is just, yeah, well, I mean, it should be straightforward how to do it, but again, that's not what I'm trying to test you on. It's more the, what happens after that. So this is just one of the sample data sets that are available natively to Google Colab. So I just pulled this in from sample data and it's just California housing. And I just wanted to show an example of what it would look like if we were to take sometimes it's called like a simple random sample or like SRS, which is just like a random sample of, let's see how many observations we have here. So we have 3,000 and let's say, hypothetically, this is the population of data and we now went and took a sample of this and I wanted to run an experiment to see, if houses that are manufactured more than 100 years ago, sell at a higher price than houses that are, manufactured since 100 years ago. That was some type of experiment I wanted to run. I would want to take a sample of observations from both of those classes that I'm looking to compare to, run a hypothesis test on it. So this will be similar to what you'll see in the final, where it'll start with a data set similar to this, and I will create a new subset from this. So let me just call this, simple random sample. So I'll take the data frame and use this sample where I will say like how many observations. So this is like the sample size. Let's say I wanted to take a random sample of 25 observations. And I'm just going to demonstrate this whole setting seed principle and what this would look like without setting the seed. So this just created a new random sample where now, oh, okay. Copy and paste that. We see it's 25 rows. I just kept printing that. It's 25 rows from the entire data set, but I didn't set the seed. So what do you think would happen if I ran this again?
It would give you 25 random samples.
Yes, but what would be significant to that if I were to run this again compared to what I have right here?
There would be different records returned, possibly.
Yes, exactly. So just by running this again, and maybe, even when you're doing your analysis, maybe you want to go back and like start from scratch and you found some type of conclusion, and you're like, oh, I made a mistake. I got to go back and rerun it. Now I won't run this again. So yeah, you'll just see now these are different values. I just reran the head now instead of the index, being 2000, now we're at 765. So exactly, Jason, what you said. And also what was mentioned, yes, you're taking a new random sample, but it's a different one compared to if we set the seed. I think this is the syntax for that, which you can check by hovering over this. Oh, it's random state. And some other things, with replacement, if this was like a Bernoulli distribution and we didn't want to have replacement, we could also have that as a parameter. But I think by default, it does not replace the observation. So it just takes and doesn't replace it back. So I think it's random state. But that's synonymous with this seed. If we use the random package and set the seed in that way, I always use 42. That's the answer to life. So now when we run this again, let's see what shows there. And if I were to run this again, let's see now, it's the same exact one. So this relates to reproducible research. Now I can make sure every time, I run this analysis, it will show the same random sample again, so that someone can take this discovery I made and reproduce the results to either confirm or, dispute what I did, or also like to add on to it to say, oh, they found this discovery. Let me now try something else and progress scientific knowledge even further, compared to if we're all just doing our own thing, not sharing any of it, we all lose out on progress. I see a hand raised, Mara.
Thanks. So how does changing the seed change the data, or is it more of an anchor where it like tells whoever is reproducing that data or also doing research, like what our sample size was?
So the sample size is defined by this parameter. So we're saying I took a sample of 25 observations from this data frame, and this parameter of setting the seed of the random state, what it's doing is it's instantiating where this random selection will start from, and saying start from this starting point, so that every single time I take a random sample, it is starting from this point, so that it's returning the same random sample. Because I don't know all necessarily like the computer science behind how this algorithm works of taking a sample, but it essentially has like lots of random numbers generated and creates like an index to say like, okay, plug this one, take this one, and return it in this order of randomness. And that's why setting the seed starts that anchor of like, start here and take randomness from this sequence.
Okay. So the seed amount is not necessarily the size of the sample or a specific data point.
Right, it's just saying, start the seed from this, this arbitrary number. I could make the random state, that, and every time I run it for there, and I'll leave this open here, this is something different, but if I went back to 42, I would expect to get back, what I saw here. And I probably could have labeled these better just to demonstrate, but I'd say like, play around with this stuff, see how it changes. Because now when I go back to 42, now it returns this. So just to succinctly answer that question, this 42 has nothing to do with volume or amount. It's just a random seed of instantiating so that you can recreate the same random sample from the data frame.
Okay, so that's actually part of reproducible data, right? So if I'm also an analyst and I'm trying to get the same results as you did from a data set, I would also set the seed at the same number so that I could try to reproduce your data. Is that
Yep.
correct?
Exactly. And that's why having a link to the original data is also part of that, initiative for reproducible research.
Okay, got it, thanks.
But yeah, exactly. All these concepts tie into each other. And even also getting to, if you were an analyst and you wanted to, validate this, you'd probably want to run a couple of samples. And so you'd want to be able to get those different amounts and compare them.
And I think reproducing data is a huge part of the legitimacy of one's research, right? So that's the whole point of like creating these parameters so that other people can check how legitimate your research is, right?
What do you mean by how legitimate?
Just let's say we were doing a medical test and you'd want other peers to be able to reproduce your research to verify your hypothesis, because your hypothesis might be based on the efficacy of a particular drug or the efficacy of a particular treatment, right? So like reproducing that research is critical to the credibility of it.
Exactly. And that's why this concept of like falsifiable is what we started this whole semester talking about. Like you make a claim, but it needs to be falsifiable because someone needs to be able to collect evidence to prove that claim true or false. And that's what we learned how to do through this hypothesis testing, to say like, I have this claim, let's create some sample to test this from a population that serves as a proxy to either, be evidence to support my claim or refute it. But it needs to be something that can be reproducible so that I can't just say, hey, I found this crazy thing, but no one else can reproduce what I did. That's not legitimate, perhaps as the word you use, like research.
And falsifiable is one of those double negatives, right? Like what was the other one we were discussing?
Yeah, like
fail to reject. Exactly. So falsifiable just means you're able to test whether the results are true or not, right?
Right, exactly. I was just getting some photos up because we were talking about, I think it was Karl Popper who brought up, yeah, it was Karl Popper, about theories and how do we test things. So exactly, Mara, what you were saying. It is kind of like this double negative of like falsifiable means that we're trying to prove it true, but it needs to be able to be, kind of reductionist thinking of like, we have this plot or like this theory, how do we prove it true? Well, like we need to prove it not false in a sense. So this gets a little bit more into like the theory of these things. Of like, what is scientific discovery? So yes, I like the things you're bringing up. Any other questions relating to this? Because this would be one of those theory related questions of, talk about sample size and use one of the case study questions as a, as supporting of whatever definition you say of like, what is sample size and why does it matter? Okay, great. So the other concepts we wanted to talk through are a little more technical, but I want to talk about it because it gets us into some other concepts. But maybe before we get into that, I saw there were some other questions. So let me just make sure we track it here. I'm just copying and pasting from the chat. And we have confidence intervals, so we can get to this after. And then we can talk a little bit about quality control charts too. So we'll keep going in this order. Feel free as more things pop up to put in the chat, or we can also just keep organically talking through things. So next we'll be talking what is the difference between using OLS and ANOVAstat. We can go through this somewhat quickly because it also relates to what's the difference between PAIRIZE and using these other packages. Do you use one or the other depending on the form of the data? So we will talk through this. And for now, I will import this package that we use to use that other stat, .res that was being referred to here. So just one thing to note, because it's not by default imported in Colab, you'll need to install it every single time you restart, the virtual machine, because that's, I saw Mary, you had a question actually about that. Like, why do I need to keep uploading new sample data? It's because Google Colab is a cloud environment where we don't need to download any software, but it doesn't remember anything you did, because that would be really expensive for Google to do for free. So we have to do that every single time. And I'm just doing that so that we can have this package and talk through the difference between some of these things. And I have this prepared at the end because there was one of the questions that I recommended studying that relates to ANOVA, where we did a one-way analysis, and Tukey's honesty, significance. I forget what the D stands for, but probably distribution. So we are going to talk about how are these things different. And this was just what was provided for in the homework solution. So that's just what's copy and pasted here. And then I have the question that we're answering here. And I just wanted to simply show like how they compare to each other, and we can talk through it a little bit more. And really, I think the crux of this question was, do I need to choose one or the other depending on the data? And the answer to that is no, they are equivalent. They just can be measuring different things depending on what you put into it. And getting as to the why they're equivalent, like why would anyone create something that already exists elsewhere? It's more so, again, this theme of there's lots of ways to peel a potato. And the package for OLS from Stats Models does a lot more based on statistics and like regression testing. And I'll show you what that looks like, because I think it's really powerful for us to talk through, and we're right there. If we had one more week, that's what we would have learned more about. Compared to this model from like RES, that bioinfo kit, which was created for specifically like biomedical research, and it gets a lot more into medical testing. So I have some more information about these different things. And it's pretty much just saying this was a tool that was created to just make it really easy to look at biological data. And we just happen to use it because it does make it easy for the stuff we're doing, compared to using something from the Stats Models package, that's .stats, which does a lot more, that's just stats focused. So in short, they're equivalent. It doesn't matter what the data input looks like, because you see we actually, the parameters are pretty similar. It's just someone created a whole toolkit that's just for like biomedical research that we used for ANOVA, but it does a lot more other biomedical research stuff compared to someone else who made the Stats Model package, which we use this ordinary least squares model, which is a regression. And then we run this ANOVA, I believe this probably stands for like linear model. Let's see what it stands for. Yeah, for linear models. And we're running this model into our ANOVA. And the difference here, so I just am running it using the OLS approach where we have type 1. So this is just, if you're curious in this stuff and it fascinates you, I'd say like keep reading documentation for what goes in here and what are the parameters, because there's lots of other stuff that we could get into. Maybe this gives you the chi-square, the F test. Like there's probably a lot more things that we're not leveraging just because it hasn't come up yet. So there's always more to explore, but this type thing actually starts to show different things. Oops, I need to download this. So I'm just going to run up here. This was from the Buggies example. And in this case, just to repeat some of the things we talked about, we can use just stack rather than melt because it's just one column and we don't have that garage of the second column that we're comparing. So just to show you, this looks exactly like what it would look like if we melted it. So we can use either approach. They're equivalent this time around. So it's just to show you that. And I just need to run that so that I can have the data here to show that when we, I didn't change the column name. So it's saying, I have no idea what you're talking about because I'm basing off this, and it automatically named it level 1. So I renamed that to production and 0 to line to make this a little bit more interpretable. So now this is what we're working with. And therefore, when we run it down here, we'll see these, you know, we have our F statistic, we have our P value here. We have what the mean squared difference is, our sum of squared, degrees of freedom. And we have the same exact information if we use that bioinfo tech package with the stat, and we have the same exact thing. One difference, if we then use this type equals 2, you know, it gives us slightly different information. This doesn't give us the mean squared error. You know, so it's just like, depending on what you need. And then if you do type 3, it actually gives us this interesting thing of the intercept, which is based off of this ordinary least squares regression model. And this is the tangent I want to get into slightly, just to expose you to regression a little bit more, because we've touched upon it. So this is not on the final, but I really can't help myself. I just want to talk about it. Because it'll kind of show like why some of these packages and why using a software like Python or R is so powerful, is because you can do lots of quick analysis on data. So this is just a housing case study where we're looking at medium house value, you know, comparing different variables. You know, if I wanted to predict housing values in different areas, I might use these input variables as predictors to say, like, depending on the median housing age, what will the house value be? And this is relevant because this, you know, relates to the data we saw in the midterm where we're looking at housing prices and trying to understand, you know, what are the key drivers that might increase the house sale price for different locations and variables. So we see here, if we were to plot this, there doesn't seem to be any relationship. You know, we're not seeing any linear patterns. We're just seeing pretty much noise where it doesn't seem to be any like real relationship between the house value and median age. So that would be something I would caption below this. I'd say, you know, I don't see any linear relationship. But let's say I looked at this other variable of median income, and this looks very positively linear of a relationship, where maybe based on just median income alone, I could actually predict what will the house value look like for that neighborhood. And maybe this talks to like socioeconomic differences and all the inherent aspects of housing rooted in, you know, United States policy. This is not a policy class, but these types of statistics and analysis could maybe get into this question of like housing affordability and what are the different things that actually relate to the value of your house. So talking about this, because I see this linear relationship between these two variables, we can use something like linear regression, which is based on this OLS model that we're actually running for our ANOVA on these two variables. So again, I'm just talking about this just to really show you the power of the things we're learning and how it applies to real world scenarios where we have this X variable of let's predict the median value using median income because we see this linear relationship. So I'm defining my X of the independent variable and the Y as the dependent variable and just defining these. If this was a class, we would talk a little bit more of to why we need to do this add constant. Just for sake of time, you need to do this in order to create this type of regression model, which we use that same exact like OLS. It's a little different here just because it's calling something else. But it's essentially a similar thing of like we're fitting the data and now we could print a summary, which gets into, this is regression. This could be considered machine learning in a lot of ways it is, because it's trying to take data and use what happened in the past to predict or inform, future trends. And using statistics, we now can start to put a measurement to what is this relationship? How much would the median house value increase if the area's median income were to be, I assume this is, hundreds of thousands perhaps, to say, this difference in median income creates what difference in the median house value. And we now have similar statistics we've been looking at when we have these p-values. We have it here. And also this t-value, these confidence intervals to say from this tail to this tail of the area under the curve, what would this model look like if I were to run this on perhaps new data in a sense? So we have this constant here and this variable of the income, but really I'm just going to synthesize this and say, this is our essentially, oops, this was from that other model. I need to just run this again, because now we're getting into this intercept of the y-intercept and the slope. And now we can, similar to when we made that first scatter plot and we just had that line where we ran it through, I can now use this model that is the foundation of ANOVA, of this like fitting a line to minimize the amount of error of like this mean squared error, to create this model that can capture that linear relationship and give you a general sense of how you would expect the median house value to change given the median income. So this just takes what we did in class and just extends it a little further, but hopefully that was somewhat relevant and interesting to the class. Any questions relating to that? Okay. And then just getting to the second question, because we pretty much already touched upon this. They are equivalent of what's the difference between pairized versus Tukey. I don't need to belabor this point much further. There's more than one way to peel a potato, and they give us equivalent things. It just might be changing the order around. It might be changing the polarity. Is this positive or negative? But really it's just comparing the differences. So it doesn't matter if this is a positive difference or negative, it's still, a delta of the same value. So in short, these things are equivalent. There's lots of other ways to maybe calculate some of these things. What's important and what we obtain from this class is how do we interpret this p-value? And, you know, if we had a hypothesis test, we'd be able to use this to either accept, you know, or reject the null hypothesis based off of our understanding of statistics. Any other questions, just even relating to ANOVA, to this pairwise? Because there will be a question on the final that is asking you to do, you know, first a one-way ANOVA, and then, you know, if you reject the null hypothesis and you find, hey, there is some difference in the variance between these groups, and now we want to know, okay, which group is causing the difference? So then we do this pairwise comparison. And so this would be that second test we would want to run to say, okay, which one actually had a significant difference? Okay, so no question. Yep.
Can we go over the Tukey test real quick? And when we're supposed to use it?
Sure. So you would use this Tukey test because it is creating that pairwise comparison between groups to actually calculate which group had a significant difference from the other. So when we do this one-way interact with ANOVA testing, it doesn't even have to be two-way with interaction. Just ANOVA is a zero-sum game where what we're testing is just the variance between groups and the variance within groups. And we are just testing, are the means equal between these groups or are they different? And we run our test, we compare the variance, and we would either conclude, hey, we found a test statistic that is so significant that it could only happen by random chance, 1 out of 100 times if we're 99%, confidence interval for our alpha 0.01. So we would say, okay, the means are different, but which mean is different? If back to like this store sales example we covered in class, you see, okay, between these 3 different store layouts, I saw they're not equal in means. So one of these store layouts gives me more money, but the question is which one? And so ANOVA is limited where, again, it's just comparing all of the means compared to doing something like the Fisher LSD, which is similar to the Tukey's HSD. It just is more susceptible to false positives just because of how it's calculating the pairwise comparison. But in an approach and methodological way, it's doing very similar things. It's taking the means between groups and doing this pairwise comparison so that you can then be a level deeper to say, okay, I know the group differences are significant enough from the ANOVA, but now I want to know which one, so I can use Tukey's test to find out which mean difference is causing that significance in the ANOVA test. And therefore knowing like which of the store sale layout had a higher sale outcome as a result of this experiment I ran. Did that help answer the question?
Very much so. Thank you.
Perfect. And that also, even just to tie it back a little bit with some of the things we talked about tonight, because that would be getting at this analysis of variance of how different is brand A compared to brand C, and is this mean value in years significantly different enough? And using the analysis of variance, we can just test, does brand have a significant impact on how many years a car lives for? And we test that. And then if we wanted to, if we found, hey, there is a significant relationship between brand and the years, then we would want to take that further and know, okay, brand C is more than brand B, and that's significant, but maybe between brand C and brand A, the means just aren't different enough for us to say with certainty that there is some meaningful difference between the average amount of time that a car will survive between brand A or brand C. So even getting just like all the way back to what I was first talking about, if you were a car salesperson and you wanted to give your client, the best information, you would say, between brand C and brand A, if you keep them both in a garage, it's going to have the same longevity. So, you should go for whichever one's cheaper. Alrighty. So we got through the rest of the first 4 questions. And we'll talk a little bit about confidence intervals relating to statistical inference. And this type of question just relates a little bit more to when we are calculating that p-value and when we are defining that alpha. And I'm going to draw again, because this confidence interval, actually, it all kind of relates back to, like what threshold are we cutting ourselves off at to say, I think that the mean here, like, let's just say, this is kind of getting a little bit outside of hypothesis testing and getting back to when we were trying to predict, your Amazon, and you want to say your package will get to you within 5 to 7 days. They have this confidence interval that your package will get here between here and here. And it would be almost considered an outlier for you to get your package, the very next day. Let's just say, in 1 day, and you would call to complain to say, hey, it's day 7, or, it's past day 7. Let's say it's 12 days and you haven't received the package yet. This confidence interval did not do a good job capturing the true outcome of how long it would take for your package to be there. So when we change this confidence interval to make it more narrow, if I wanted to be so precocious and say, you will get your package in 3 days at 3:30 p.m. and that would be a very constrained confidence interval. So even if you got that at 3:50 on Wednesday, I would still, be susceptible to a customer complaint saying, hey, you told me it was going to be within, this interval and it's out of that. I get to, complain to you. So, when we constrain the confidence interval to be tighter, it means we're more confident that the value will fall within here. And that gives us this level of precision. So now, okay, instead of 3 to 7 days, I know it's exactly going to be right here. But it also, could create this potential for getting it wrong to be higher. So as it relates to statistical inference, when we are making these conclusions and setting our significance value to be, like 0.95, we are taking this concept, but almost like flipping it to be in the tails now, where we're saying that our confidence interval, let me draw a new picture just to show how I'll leave it there. I'll choose a new color just to demonstrate this concept. Let's make this blue. So now let's just have an example. I'm comparing the mean house price between, I might conjecture the mean housing price in New York is 100,000, and I have a sample to compare housing prices, and I'm testing, is the average equal to this value as a mean hypothesis test. So I say, the mean is equal to 100,000, and we ran a sample. We took an experiment of a representative number of observations for housing prices, and we saw that the average price was actually, 500,000. So this is a few, standard deviations. If we knew like what is the mean and the standard deviation of what we would expect from the population. And then we ran an experiment and our sample mean or X bar was this, we're using this value of a confidence interval to see like how far away is this from the mean. Let's just say like standard deviation was 10,000. So maybe this relates to like a very potentially like just a very homogeneous neighborhood where all the houses are very perhaps, affordable and pretty much everyone can afford a house. It's 10,000 below or 10,000 above this for one standard deviation. So like most of the houses are, within this interval. And if we use, like Chebyshev's theorem of saying like what proportion of observations would we expect between like 2 standard deviations, 3, so on and so forth. But we saw a value of this from our example. So based off of this, we could calculate that this is, let's just say 5 standard deviations away from the mean. So it's, something like that of how many standard deviations from the mean it is. I'm just trying to draw a little sigma there. And this is a 5. So we're getting a value that's like all the way in the tail. And because it's so extremely different than what we thought it would be, and we set our significance threshold to say 0.95 or the alpha of 0.05, and we would actually divide this by 2 because it's in both tails, because this is a two-tail test, because we're comparing is the mean equal to this, because it could have, also found a house observation that was, let's say, just to be in scale, let's say we saw a house that was $20,000, and this still would be evidence to reject the null hypothesis that the average was $100,000. It would just be in the other direction. So, and we found, just getting back to the example I was talking through, we found a value here, and it is so far away from what we would expect. It is 5 standard deviations away, and it would be past this area under the curve of what, test statistic we would have needed to just pass this threshold of 0.95. So it exceeded that. Therefore, we are confident that if we were to run this experiment 100 times, we would only expect to see a value this extreme 5 out of those 100 times, just due to pure chance. But we did see it. So we could say we saw this value and it was over this threshold of 0.95% confidence interval. And therefore, we can reject our null hypothesis based at this threshold that we set. But if this was something even higher, if we wanted to even have higher precision, or let's say this is kind of just related to that window of your package getting here right at 3:30, let's say this was something we needed to be even so much more precise and like certain that we're not just getting this due to random chance in this observation we saw being so high of this sample mean. Maybe we just took a sample that was biased and we only looked in like the really expensive fancy neighborhood, and we didn't make a representative sample of like every single house, in this neighborhood that we're trying to represent through a sample. That could be some potential reasons you might have like a false positive or a false negative, like these type 1 or type 2 errors. Maybe, the sample wasn't representative of what you're really trying to measure and you like cherry picked it. But anyway, if we wanted to get this 0.99, this value would then need to be at an even farther threshold because it's even less area under the curve. So we would need the value to be over here, like in the tippy tail, to be able to say with confidence that only if we were to run this 100 times, 1 out of those 100 would expect to see a value this extreme due to random chance. But we saw a value this extreme, it passed our threshold of 0.99 significance, or an alpha of 0.01. Therefore, we are very certain that this hypothesis can be rejected, and we would we would reject the null hypothesis to say the average house price is not equal to $100,000 because we found an average price of this, and it's so far away from what we would expect, and just, natural variation due to, how variance exists in real life. You wouldn't expect to take a random sample and for it to be exactly 100,000. Maybe it would be 120,000, but that would still not really be significant enough to find evidence to reject the null hypothesis. Because, this would still be within the expected number of standard deviations from the mean for us to say, this isn't enough evidence, but we saw something all the way over here, and we would only see something like that just due to random chance 1 out of 100 times, but we saw it, therefore we found a discovery, and at this threshold, it's significant. I definitely went on a long tangent, but that answers this question.
Yeah, I want to just take a few takeaways from that. So can you just go back a little bit to once you did the calculations, the confidence interval, what was the number that you looked at to come up with that insight?
The number that really matters here is, are we looking at a very wide confidence interval? And this does get a little more confusing compared to what I was first saying, because it's almost like when we shrink the confidence interval here of saying we're going to get a package, right in this time, this is kind of equivalent to saying you saw a value and it's so extreme, and we're being even more precise in how extreme it is because we're pushing this further to the tail. So this relates back to whatever threshold we set. If we said 0.90, 0.90 significance threshold, this would be area under the curve is, 10% of the area would be in both tails. So we're almost reducing this confidence interval to be shorter. And it almost makes it so that more, the value doesn't have to be so extreme for us to still make a conclusion of a discovery. So in that case, back to the house prices, if we had the confidence interval at 0.90, even if we saw a value and it was only 3 standard deviations from the mean, we might still say, hey, this is significant enough for us to reject the null hypothesis, compared to if I wanted this confidence interval to be more narrow, to say it needs to be so extreme that it's all the way in this tail, then this value would go up to be 0.99. So we're kind of saying how extreme does this need to be in order for us to feel this is reliable enough? And it kind of relates back to this area under the curve, and the likelihood of seeing a value goes down the farther you get away from the mean if it's normally distributed.
Will z-scores and t-scores be on the final as well?
So when you are creating the test statistic, you're essentially calculating that value of, that is essentially what the test statistic is. It's like a z-score in a sense of how extreme is the value you saw relative to what you would expect to see. And if it's past that of the p-value, then we can reject the null hypothesis. So you won't explicitly be asked calculate the z-score. It will just be part of the steps, and it's been part of what you've been doing all along anyway with calculating that test statistic. So just depending on the distribution, if we're calculating the difference in means, you would essentially be calculating that z-score for the test statistic.
And the t-score is the z-score represents the ends, right? And the t-score is the part in the middle, kind of the part you have highlighted there that says 830.
So the difference between z-score and a t-score, this actually depends on the distribution we're using. And this t-score, think back to like student t with like those t-tests, and when we have a small sample size, we need to use the t-distribution. But when we have normally distributed data, we would use the z-score because we can use the, the z table. So kind of just depending on what hypothesis you're testing, it changes the test statistic you need to use. And these are the differences between z-score and t-score. It's not talking about the same thing. It's talking about different distributions. I mean,
Okay.
it is talking about the same thing, but in different distributions. It's not two different parts of the same distribution.
Okay, just making sure.
Any other questions?
I have a quick question.
Sure.
So, can you just tell us, I guess, so like the p-value, if it was less than the alpha, can you just explain like what that means in general? Like if we were like relating to an example that you have maybe of like, I don't know which one you have, the garage one. And then I guess explain if it was greater than, like both, just so I know like what you really mean, like a full explanation.
Sure. And this
Yeah.
is really pivotal to our class and what I would really want us to be able to walk away with as a result of this semester of like, what is this p-value? What does it mean? So I really appreciate this question. And I will use this example where it kind of relates to what I was just talking about with this area under the curve. So let's just talk through from start to end where, you have this question of, someone makes this assessment and says, past year home prices, increased. I am trying to conclude if the houses in this area are greater than the houses in the other area. So we would be trying to test this claim, which is trying to claim that the housing is greater than this value. So let me just back to our distribution picture, because this will tie into like, what is it when we say the p-value here? And we'll bring it back to an example. So we're trying to compare this mean value of 6.6%. So don't worry too much about this being a percent. This could be 6.6 years. So I think percent kind of gets a little confusing because it's like, are we talking about proportions? We're just talking about, 6.6 units. And we want to test based off of this experiment of n equals 36, because we're taking 36 observations of home sales in the West. And from this experiment that this realtor collected, the home price was actually 7.5% with a standard deviation. Because again, this is, a sample where we have more, it took 36 observations. And, if we had like a histogram, we would see most of them had 7.5% home price value, but some of them had a little bit more, some of them had a little bit less, just at this 2%. So just even thinking about what it is we're looking at, this is I'm just going to draw again, if we were just creating like a histogram of what this prompt is telling us, this is dollar for what the price is. And let's assume, this is normally distributed. So I would have, the price be equal from what I found in this experiment. Let's call this experiment. what we saw was 7.5 with a standard deviation of 2%. So, you know, one standard deviation away, we would just add 2 to this. And, you know, we would have the 2, and then we would subtract 2 from this to be over here. So, and that would be, you know, 1 standard deviation, 2 standard deviations, we would just double that amount, 3, and so on and so forth. So we would expect the distribution to look like this. And we're essentially now comparing what the claim is to what it is that we saw to be able to either find evidence to accept that, you know, the West has a higher average increase compared to what was claimed by this, you know, whoever this person was who claimed this. And we want to claim this at a 5% significance level, which is pretty much just cutting us off to say it needs to be, you know, within this confidence interval, it needs to be statistically significant. It can't just be a little bit far off, you know, 7.5, let's just say that's somewhere over here. You know, we need it to be far enough away for us to conclude with significance that it is meaningfully different than what we would expect to see if we would fail to reject the null hypothesis. You know, for us to say, we didn't find any evidence that's strong enough to suggest that this observation yielded results, you know, 7.5%. This could just happen because of like the sample we took. This isn't really, you know, that we can't really refute this claim. Any questions just based off of how we're framing this question?
Is this kind of how you want us to set up our extra credit?
It could be. It could be. I mean, extra credit really is very open-ended. So if you wanted to just kind of do like minimum required, maybe just think of which hypothesis test is like the easiest for you to do. You know, if you're trying to use this maybe as if you're applying to jobs and you want to do something to put on your like GitHub as a resume builder to really demonstrate, you know, your interest in something, you know, depending on what that interest is, maybe you would want to set up this type of hypothesis to actually test something. So for the bonus, I would say like talk a little bit about what is it, like what's the claim you're making. But really like bare minimum is just you need to make a claim, you need to test it and use whatever hypothesis test is reasonable for what that theory it is you're trying to test. So no need to like get into some of these details. I'm just talking through, you know, what this would look like. So maybe even just doing a histogram of the distribution. That would be a really great way to use our aspects of qualitative statistics in addition to quantitative, where we're actually measuring the mean value and seeing if it's significantly different than our null hypothesis. Does that answer your question?
Yes.
Perfect. Okay, so now getting back to Gershni's question about next steps for the p-value and the z-test. So kind of touching upon some of the other things. So I'm going to go back to my mouse. And just from this scenario, you know, I know what my sample size is. I have the X bar or like the sample mean. I have the population standard deviation of that. And this is the hypothesis alpha mean that I'm testing for. And I am converting this 5% significance level to say an alpha of 0.05. And because this is, you know, this is a one-way, not one-way, confusing ANOVA with one tail and two tail, because we just need to compare that it's greater than, you know, we don't care about anything that's on this side. So that's why we don't need to divide this area under the curve in the tails of what we're looking for by 2, because really we're just looking right here at this tail and seeing if this value is far enough away from what we would expect to say this is a significant difference in means based off of this sample we took. So we use the z-score, back from when we just were learning about continuous distributions and creating, the probability of seeing a value given a mean and standard deviation. We are using that same exact formula using the value we saw in this sample of 7.5, the mean we're testing against, and this standard deviation of what we saw in our sample, and dividing it by the number of observations. Again, just talking about if we took a larger sample, we would be dividing by a larger number and not necessarily like penalizing ourselves as much. So this is just something to consider of, okay, sample size is being used in our test statistic here to get the z-score of how many standard deviations away from 6.6 are we? Or, what would we be expecting to see given this sample compared to what we would expect to see with that standard deviation? Oh, okay, well, don't mind some of the drawings here. Maybe can I? Erasing some of that just so we can talk through some of these things. So now we use this p-value to convert that z-score we found into area under the curve. Or sometimes people might say like, this is like probability of seeing a value, at least as extreme as the value we saw. And given, how many standard deviations away from the mean. So these are all pretty, like, I guess another theme of this class is like two sides of the same coin. This z-score is kind of giving us this threshold. And now the other side of that coin is area under the curve, to say like this p-value is 0.0035. And that's how much area under the curve is filled in by this value. And therefore, let me just use another color here. If we set this threshold of what we would expect to see, this is now just summarizing what is the point of this significance value we set here of this alpha. We are setting a threshold. If this was, 95% confident, then we have 0.05 area under the curve. So this is before we even test anything. That's why we continue to see these values of, 90, 95, and 99, because it's all about the tails. And so we set up this as like our hypothesis framework to say, okay, whatever test we do, it needs to be so extreme that it passes this interval, this threshold, and is in this area under the curve using statistics and probability because of the distribution and how frequent we would expect to see a value at least as extreme as the one we saw. And we saw a value that was even smaller than 0.05 of this area. So that means it was even smaller in the tail. So let me draw another, what this would mean is we saw a value with area under the curve over here. So it beat our threshold. It's smaller. It's smaller than what we set it as. So even if we were to lower this threshold, and let's say we even wanted to be even more confident, so getting back to the question before of like, if we wanted to be very specific about, when we would expect to receive our package, we're making this confidence interval even smaller and saying, this is so small, it would have beat our 0.99 or 0.00. Okay, but it wouldn't beat that because this was actually larger than that. So it's not so small that it would beat, this 0.99, but at the threshold we set it at, it was smaller than this. Therefore, we found evidence to reject the null hypothesis. So that's why we have this little setup to say if the p-value is smaller than this threshold of alpha that we set it at, we found evidence to reject the null hypothesis. So can someone just tell me how this relates back to this distribution we talked about? And maybe just like summarizing what it is I said, like as it relates to, we thought we would see this distribution, but given the data we saw, it looked something more like this, and we tested it. So like, what does this all mean?
The hypothesis, the null hypothesis was wrong.
Well, we found evidence that would lead us to reject the null hypothesis. So we could say, yes, the null hypothesis is wrong because we found this experiment to yield results that were higher in the average sale price. But kind of getting back, like, how did we prove that? You know, how can I say with certainty your assessment is wrong? Like, how can I be even sure that this is wrong, like that we can reject the null hypothesis?
Well, I know we're not supposed to like talk in absolutes or something like that, right?
Yeah.
So I guess we have to say it like in a pleasant way.
Yeah. I mean, it's good not to talk in absolutes because again, whatever sample we took, you know, we're talking probability, and that's why we say like at least as extreme as the value we saw. But really what I'm trying to get at here is saying how someone came up with this theory and we used probability and statistics to test what would it take for the results of our experiment to prove this theory wrong. And that's why we're using this probability distribution of the z-score, which looks at like the normal distribution, to see like how extreme is this value compared to what we would expect to see if this was true. So the reason we know this claim is false is because from running this experiment, we saw the average to be 7.5. And given, you know, the standard deviation and how, you know, how this would look like as a distribution, this is so different than what we would have expected if this claim was correct, that we found evidence to reject this claim. Because the distribution in the data we saw from our experiment yielded a mean that was so different from what we would expect to see that we have this p-value that exceeds our threshold of what is considered significant, because it was so far in the tail to be having a p-value that's less than our significance cutoff that we set up for ourselves. So, and it's kind of an explanation like that that I would expect in the interpretation side. So like you ran this experiment, this is really all that's required for full credit in the technical component. And it's just bringing it back to, okay, what does this tell us about the distribution of our data as it relates to testing a claim and either having evidence to reject this claim, or we didn't find evidence to reject the claim.
Okay, thank you.
Yeah, no problem. Excellent question. And I think that, you know, as long as that is comfortable with the class, then I feel like I did my job here, and you guys have a really good foundation of statistics and understanding as it relates to, you know, what you might need going forward in statistics class. Okay, how's everyone doing? Are we feeling like we want to keep going just to answer this last one of quality control charts?
Yes, please.
Okay,
Please.
great. And then I see we have Lindsay posted a question here. I'm just going to put it in here. can we also look at question 8? Why we subtract 1? So yeah, we can talk, well, I'd rather talk about that one now before we talk about quality control, because I think it's a little bit more related to what we were just talking about when we have this question 8. So I'm going to talk about this and then we'll talk back to this module 7 just for the sake of logical threads between what we're talking about here. So the question is, why do we subtract 1 to get the p-value in question 8 in module 10? So I assume that's one of the questions I have prepared here. If not, I can just grab the homework, but I think it was this one. Question 8 in module 10. Yep. Okay, and the question is, why do we subtract 1 from the p-value? And without telling you the answer and maybe just giving a little bit of a hint when it comes to how this is a little different than the other hypothesis test we just ran, can anyone guess why we subtract 1? Well, okay, maybe that's not the right hint to give. So the question is, why do we subtract from 1 to get the p-value? Maybe before I ask that.
Like in general?
Yeah, because it
Well,
is
then we're
kind of in
looking at-
general.
Okay, well, because when you look at the distribution, that's always out of 1. So you would subtract from 1 when you're trying to find the like opposite side of what it's testing, because that covers everything else besides what you're testing.
Yep, exactly. And just to repeat it for just summarization, when we are using, and just also let me show it with like the code that we have here of subtracting 1 from here, like this survival function. But Joshua, as you mentioned, like this is kind of general for what we've been doing along the way for any of these types of area under the curve questions. When we are trying to sum all the area up until that point, that is really what's returned to here. And we want everything just on the other side. So that's why in this case, we subtracted this area under the curve from 1, because as Joshua mentioned, the area will sum to 1. So we can really slice and dice it whichever way we need. And why I was framing it around this hypothesis test is because we are trying to test if these means differ from each other. And this is essentially looking, yeah, so what I was getting at actually wasn't very relevant. This is more so about if we needed to divide that alpha by 2 to test for area on both sides, not just what the question was getting at. So this is more so like, we don't need to divide this by 2 to account for area on both sides, because we are just trying to see, is this equal or not to 0? Okay, so I see follow-up. So we will subtract from 1 if the test stat is negative. You subtract from 1 when the hypothesis is trying to see if, we're trying to just see if this difference in means is greater than 0. And this would be either, it would be positive, because we would want to set this up so that means 1 is greater than mean 0, so that this wouldn't be negative. So the test stat being negative is just a coincidence. Yeah, it's more so just you would want to start with the higher mean and subtract from the lower, so that we're testing something positive.
Can I ask how we got that hypothesis right there?
Yeah. So this question is testing if the means of 2 populations differ. with this background of knowing that the population variances are unequal. So this is the test statistic we're using. And the question is, how did we know these are the hypotheses to test? Because we're essentially trying to see if the difference, so if the means, what is the question? We're trying to test if the means are different. So we would need to first say for our null hypothesis test that the means are the same, but we can't necessarily, because the population variance is different, we can't necessarily just test that mean 1 is equal to mean 2. Similar to how we did in some of our other hypothesis tests, like just one of something like this, where even if we wanted to test, is this equal to 6.6 or not? This is what we learned in module 9 of hypothesis testing. And then in module 10, we extended this to when the population variance is unknown and can't be considered equal. So we use this t-distribution. So we are now testing if the difference between these two means is large enough to find evidence to say these are not equal to each other. So it's overcoming this limitation of knowing about the population variance to say, let's just say the mean of this group was 100 and this one was 100. If we subtract, 100 from 100, we would get 0, which would essentially be evidence to say these means are equal. And the claim we're trying to say here is that, the sample, there is a meaningful difference between these two samples. So we would calculate the mean of these two things and using like the sample standard deviation to calculate this test statistic. And if it is, if this mean is, 200 and this one was 20, and this was so extreme from what we would expect to see given, the standard deviation and the sample size, this difference is so great that we found evidence to reject the null hypothesis, to say these means are not equal to each other because the difference between the means is not equal to 0. And how much is it not equal to 0? That's why we have this test statistic and compare it against our p-value. And if it's so extreme that it's, in the tail of what we would expect to see past our threshold of, 0.95, then we would have evidence to reject the null hypothesis at this level of certainty. And this connects why we need to set up and frame the hypothesis tests in this type of way, is really because of the tools we're limited to with testing the differences in means, kind of given the assumptions that we take for a normal distribution compared to something like this, where we have, a smaller sample size and we don't know if the variances can be considered equal. So we need to use a different distribution. We can't use the normal distribution. We have to use the t-distribution. And this would be somewhat similar to using like the F distribution. It's kind of like, depending on what it is we're testing and what assumptions do we need to make, would inform which distribution we should use. So in the final, it will be mirroring one of these examples that are in this final review notebook. And so you should be comfortable taking these steps and just applying it to new data.
Perfect.
Okay, cool. So Lindsay, does that answer your question?
Yeah, I think I'm good. Thank you.
Okay, perfect. So Now we will talk about this question about quality control charts. And this is a good question to ask because actually on the final, all of the case study questions will be from the same data set. And so a lot of the quality control related questions we've looked at is more about like a production process and comparing, you know, even like those bowling scores to what we would expect to see given a normal distribution. In the final, we'll actually be using the same concept of what we would expect to see if we were to take a sample in, you know, time interval 0 compared to if we took another sample in our, you know, manufacturing process, but applying that to time over months. So I'm going to pre-process a data frame for you and take random samples from each month. And you will need to calculate the sample mean for each of those rows to calculate, is there any type of pattern that is emerging in this time series to suggest something is out of control? You know, if we think back to like this housing price scenario that we've talked through a couple times, you know, if we were to take a sample every month and we saw, you know, January, February prices were up here, and then, you know, in the spring prices were lower, and then in summer they peak, you know, is this some type of cyclical trend in something that's like normal? Like, are things really deviating from the mean? Or maybe there was something like COVID and everyone is leaving the city and inflating prices in other areas. So we see this like outlier of a trend in, you know, whatever month we see like a skyrocket in prices. This same type of concept of quality control can be applied to see how much does the mean value that we observe deviate from what we would expect to see given a normal distribution of values. Does that make sense before I walk through this example that we had in the homework? Just to really answer this question of, you know, what type should we expect? But just like that framing around how the quality control experiment will apply to the final. Okay, great. Because I wanted to include that as it does relate back to, you know, our area under the curve and distributions. And I think I really like how visually quality control charts look at this area under the curve. So I will use this example from the homework just to talk through that a little bit more, where we had some guy who's really good at bowling and we have all these observations. And, you know, if someone's really excellent at bowling, they will consistently score, you know, all the strikes and not have a lot of variance in how they perform compared to if I were to go bowl, maybe I'll get 1 strike because I got lucky, but most of the time I'll probably not do great. So this type of like variance and what I would expect to see given, you know, what distribution of values we would see. So something like this, let me just read in this data frame. And this will be exactly what you will see on the final. Something like this, where perhaps the only difference that would exist here is that the index will be kind of like this identifier to say, you know, for this sample, oh, and then I would want to drop the index. So pretty much you'll see like for this month, these were the random observations of whatever it is on the final that the data frame we're going to be looking at. So, you know, like for this month, these were the observations we saw in this month, you know, and we want to start to use quality control to see, are there any cyclical patterns to say something is, you know, there's a trend here. It's not random. Getting back to like for the manufacturing, like it's okay to have random variance, but if we saw, you know, your machinery was having like cyclical patterns and giving too much, you know, pudding in a pudding container consistently in a weird trend, you might think, okay, maybe there's some type of calibration error in the machine I need to look into. So just taking that concept, applying it to time series. So just giving you a little bit of foreshadowing of what you can expect to see tomorrow if you plan on taking it then, where you would need to create this X bar of the sample mean across the observation columns. So we would see something like this, where we knew for this one. Okay, let me just make this a little bit more clean. I think I'm just, by saying make it more clean, I'm just gonna say like set index to be sample and then drop equals to be true, which I'm pretty much just saying, you know, like set the, it is pretty equivalent to what I just had, but now I'm dropping that column to say set the index, because this will just make it a little easier for us to graph things and for us to see. So now for this bowling experiment, you know, he went bowling 4 times, took the number of observations for, you know, whatever, 6 times, took the mean, calculated what we would expect to see for calculating these upper control limit and lower control unit. And why I say this relates back to our histogram and distribution is because this is essentially just showing us in a different way, you know, what this mean would be of X, and then pretty much saying, take this mean and add 3 standard deviations above and below to test what would be considered like an outlier almost. To say like, if we saw a value that went beyond what would be expected, and we saw something in the tails over here, you know, this would be considered an outlier. And if we were doing like some type of hypothesis test to say, you know, I don't think this bowler's average is, you know, 94. Maybe I think this bowler is actually, he's like, you know, I think he's more mediocre than he thinks he is. And then he tested this, you know, and maybe he scored a 60. That would be evidence to say, you know, it's not just normal what that output scored. It's so far away from what we would expect to see. To the left, you know, this bowler scored lower, and therefore, you know, we would have evidence to reject the null hypothesis of saying, you know, the average was this, and we ran an experiment. So this just brings that concept into saying like anything that this bowler bowls within this area is kind of expected. And we would see this, you know, if this was a really precise bowler, most of the values would be between these 2 things, and the distribution would look more like this, where like the average is here. And most of the time this bowler scores anywhere between here and here. So like 3 standard deviations here. I'm getting into, I think, a little bit more context than necessary. Getting excited. So bringing that just back to the question of having these control limits is we're pretty much making a threshold of what would the value need to be in order for us to say what this person bowled was like an outlier. It was so different than what we would expect to see, because this is our lower threshold and our upper threshold, because it's taking that mean and adding and subtracting 3 standard deviations from that. To pretty much say, if we saw a value that exceeded these control limits, that, you know, your machine is producing something that is anomalous, you know, is either like a defect, you know, this pudding machine, there's only like 2 drops of pudding. Someone's going to be very upset when they open their container, or the container is totally stuffed with pudding and it's going to break, you know, the machine that weighs it. So you have a problem and it's not within, you know, this specified variance. So, and we have this control chart to see, you know, if we saw a point in one of these observations that goes above or below these control limits, we would say, you know, this bowler is out of control, or this process is out of control, or, you know, thinking back to those housing prices, if we saw, you know, what happened from COVID compared to a year ago, if we were to take, you know, this trend line in prices, and are we seeing something cyclical? Or are we seeing this? And then it's like, pew, something went down there and then we got here. You know, this is what we would expect to see but we saw a value that exceeded this normal distribution, and we could say this is out of control. Some other things to note would be like, are there cyclical patterns? Because that, if this was just stochastic and randomly distributed, we would see something like this with no real pattern. But if there's something seasonal or like a trend, then this might relate to something else going on, and it's not randomly how this person's bowling. So maybe, if we saw some type of pattern here, maybe there's something afoot that they're, continuously, maybe adding like soap to the ball to make it go faster, or something weird where like a pattern is going on. Because like every time they bowl this time, anyway, I'm just talking like hypotheticals of other things that might be going on. So really just getting back to what's really important here, as long as you feel comfortable running these steps, you will have all of the technical code necessary for answering the question, because you'll need to create a control chart and just say below here, just one line. And then the written interpretation side would be, like talk more about what this means, interpret the results and summarize it in some meaningful way.
Can you share some insights about the chart?
Yeah, sure. So just from this example, I would want to talk through like what this average is and how the upper and lower control limits are essentially looking into like what would be expected under a normal distribution of values. And if we saw, the pattern stays within this limit, and maybe even if I wanted to say like, hey, this bowler keeps consistently getting 94 of the bowling speed, we would know that this person is pretty consistent and maybe like just really bowls tightly compared to if I were to go bowling, my bowling speed would probably be like all over the place, and I wouldn't be necessarily like consistently excellent like this is. So something to say is just like how much of a variance do we see along the mean? Because that might say, how different does the value change month to month? So if we were to see something like, this month, the value is here, the next month it was all the way here. So I think I'm feeding a fed horse a little bit there. So that's something you could talk about. Another thing is if you do see any seasonal trends, that would be something to note, just as it relates to whatever case study question it is. If this was looking into like stock returns, and maybe it was a portfolio of, clothing manufacturers, maybe like every spring, and this was over like 7 years, we would see like every spring, sales go up compared to winter, sales are down. Like that would be something to notice as far as seasonal trends. And then of course, if any value actually goes out of control limits, then you would say, talk about how this might be an outlier and like, how does this relate to what we would expect to see given the distribution of values, or like what would be considered in control. So in short, I would say, talk about the mean and the variance around the mean and how the values fall. Talk about, are there any seasonal trends? And talk about if there are any points that fall out of control. And all of those requirements will be in the written question itself. It'll say, specifically, note if there's seasonality. So you don't need to memorize that. You just need to, intuitively be able to understand what's going on here and explain it.
Okay, quick question. How did you read the blue line as, to me, that's just like the center line of a range or just the data itself, but you read it kind of as if it was a data point.
Yeah, I like that question. So, because I would love to make this as like a histogram just to show it, but just how the data is wrangled here might make it hard for me to really show that. What if I do, I wonder what would happen. So I would just want to show like, what is a histogram of all these values? Okay, that wasn't great.
And as you're selecting what kind of graph you want to choose, can you just walk us through like your thought process on, okay, I have this data, which type of graph do I want to create?
Yeah, that's good to stop me and hear that out. Because I am just trying to explain how that center line represents the mean and how that relates to seeing if this observation is out of control or not. So I was thinking a histogram would be a good way where I'm really just trying to see, this person bowls this fast, this number of times. What I was trying to get are all of these values in one column. So I can just see, like on average, the person bowls, 82 miles per hour with a standard deviation, of +3 or below 3, to see like how spread is my data, which would relate back to that center line, which that center line, just in short, is the mean. It's saying like, this is what you would expect to see in a normal distribution. And then the upper control limit is 3 standard deviations above that mean and 3 standard deviations below. So why I was thinking a histogram would be a good visual representation of this would be because I want to see, and I'm just going to take one of these and plot the histogram compared to all of them, which gives me very sparse data because we only have 4 points. That's, kind of the point of taking this sample is like this mean is supposed to represent that distribution of values of what we would expect to see compared to if I had, like a whole data frame of all the values and I can just do, dot hist. So let me even, if this was that housing example where I think I still have that in here, just to show you a little bit more, how this would relate. So let's say I have this data value and I want to see like this median house value. If I wanted to, let's say I just took a random sample, for different ages of a house or something like that, and wanted to compare, whatever. I'm trying to take a sample between different groups. I would just want to see this histogram. And something like this would be if that, let's just say the mean was 200,000 here. We would see that as the center line, and 3 standard deviations above or below would give us the value we would expect to see. So that if we did get an observation that was somewhere in the tail, an outlier, or it was out of control, it would pass that threshold of 3 standard deviations above or below that mean value. So that's why like this center line, I want you to think, if this was a control chart, this is the mean of that center line. This is the same thing. And the upper control limit, let's take some other colors here, is 3 standard deviations above or below that value, given, the spread or the distribution. And, if we started to see some type of trend, this is just looking at this distribution as like a cadence of observations over time to see, if we took observations here and we did this experiment again, we would expect, even getting back to like the central limit theory of like, we would expect most values to fall within here if we took lots of samples. So that is how this type of histogram relates back to this visual representation. So if you could just imagine that we have like a histogram here and here, where this is the mean, and you don't pay attention to my lack of symmetry in drawing, something like this, where the mean is here. Like this would be the lower tail, and this is the upper tail of values. So that's why I really like this visual representation, because it takes these theories and just looks at it in a different way. Does that help answer the question?
Yeah, I think so. I'm just a little confused because we were looking at the bowling chart and then we went to the housing chart. So I get why you chose a histogram. So the blue line, when you said he continues bowling consistently, I only see one data point on that blue line. So how did you come up with that insight?
So this blue line is just from the mean.
Okay. Got
And
it.
so it just so happened that the first time we looked at it, that this person bowled exactly on the mean.
Okay. But since this is the mean, we can still say that he's bowling that average, and that's a great average.
Right,
Okay.
exactly. You know, that means that they scored exactly on the mean, which, you know, because this is just a little example in the, you know, in the textbook, you know, these are made up numbers. So he got like exactly on the mean. It just so happened to be that way. So yes, as long as you're comfortable with understanding like this is an observation, you know, because we had 4 rounds of bowling and we took this sample mean and we're comparing it against what the mean is that we would expect to see. And we're essentially just seeing over time, is this bowler scoring near where we would expect to see if they had like a really tight game, or are they all over the place? You know, is this bowler in control? Is there anything going on here that's like a trend? So I'm looking at the chat and I don't see other questions. Any other questions we'd like to talk through relating to anything we saw? I guess now like anything in general.
Thank you for holding the review sessions. They've been
Oh,
really,
my
really, really helpful over